Please let me. So this is the second seminar of the season, Fabio. Okay, second seminar of the season. We are starting with the joint physics colloquium. So it's a real pleasure to have today here Professor Yoshiki Matsuoka from the Ehime University. He was here at the meeting on high-energy quasars and is staying the whole week as part of the visitor program. So Yoshiki is staying here on the 4th floor in the office of Andrea Comastri today and tomorrow. He will also join the Friday AGM meeting tomorrow, so we will have a discussion to talk to him even more. And if you are interested to talk to Yoshiki, please let me know and we can schedule some discussion or some appointment. Again, as I said, in the office of Andrea here on the 4th floor. So as I said, this for me is a pleasure because Yoshiki is one of the world leading experts in the search for high redshift quasars, so meaning redshift 6, 7, probably even more, in the search and in the physical characterization of these objects through wide area surveys. He is the lead of the SHELLQ survey, which targets quasars that are less luminous than what we knew before from Sloan survey and so forth. So I think you will have the opportunity to enjoy the results from this survey as he speaks during this talk. So as I said, he is an associate professor at the Ehime University, got his PhD degree in Tokyo. So he spent most of his career between Japan and the US. Particularly, he was a postdoc in Princeton since in the years 2013, 2015, working with the Microstrauss, for instance. And then he went back to Japan, and in particular, since 2017, he's professor at Ehime University. So if you have 45 minutes, then we have questions and so forth. So thanks again, and please, the stage is yours.
Okay, thank you very much. First of all, I would really like to thank Roberto, Fabio, and many others for giving me a chance to stay here. It's a great place, really, and to give this seminar talk to you all. So as Roberto said, I was staying here for the whole week this week. We have completed the very successful high-frequency meeting yesterday, and I'm enjoying the rest of the stay. I'm slowly recovering from jet lag now. So today I'm gonna talk about a wide field survey for faint and or obscured quasars at high redshift, mainly focusing on the results from Subaru telescope. And if some of you have attended the high quasar workshop, and I'm sorry that this talk is partially overlapping with that one. Okay. So my talk will be basically on observational, practical side of the survey. So here I will only briefly touch on kind of theory side, motivation side behind the survey by finding high-Z quasars. And in this talk, high-Z means redshift beyond 6, 5.5, 5.7-ish. So by finding quasars in distant universe, we want to understand the origin of supermassive black holes, when, where, and how did they form, and how did they grow. And we also want to understand the host galaxies, which classes of galaxies hosted the first quasars, and also what was the early form of the coevolution. We know in the local universe there's a correlation between the mass of black holes and the mass of host galaxies, and we want to understand the earliest form of that coevolution. And we also want to know, okay, cosmic reionization. Okay. Thank you for yeah, thank you. Thank you. Yeah. So how did the reionization proceeded, and also what provided the ionizing photon, whether they are quasars, AGNs, or star-forming galaxies, or something else. So, for example, this is on the origin of supermassive black holes. If you find a quasar in relatively a short time scale from the Big Bang, then you can trace their estimated mass back in time, assuming the maximum accretion rate you can, assume, which is usually Eddington. So, for example, these are 3 highest redshift quasars published so far. And if you trace this mass back in time, then even at the redshift 30, the initial mass should be something like 10 to the 4th solar masses, which is almost impossible with population 3 stars. Population 3 stars could be still possible if you can keep the super Eddington accretion for fairly a long time, which
Recording in progress.
Okay. But this may indicate that some other exotic processes may be at work. For example, direct collapse of gas into the seed black holes or runaway collapse of dense star clusters. I won't explain this in too much detail, but basically by finding Heisey quasars, there are various ways to use them to probe how they were seeded, how they were formed. In addition to simply mass. For example, these observational signatures we would expect the mass ratios between black holes and the stellar populations in a given galaxy or surrounding environments, surrounding galaxies, the dark matter halos, also spectral signatures and luminosity functions. All of these are expected to be quite different between different formation models. But in order to use these probes, the very first thing you have to do is to find quasars, where to locate where in the sky these quasars are. So this is a bit brief history of how the discovery has been made with redshifts. Basically, these discoveries have been driven by emergence of new wide field surveys. For example, this is the very first one discovered at these redshifts by Xiaowei Fan and his team by using Sloan Digital Scale Survey. Its reddest band, Z band, covered this redshift Lima alpha, and this redshift record was soon pushed to 6.4 by Sloan itself, and also by CFHT, which carried out a legacy survey going down to deeper mag. But still, the reddest band was Z band, so they cannot go beyond this redshift 6.5. Because Lime alpha is still in the Z band at the redshift below 6.5, but beyond this point, Lime alpha will move out of Z band and will come into near. And this kind of barrier in redshift was first broken by near-infrared observations, UKIDSS, by UKIDSS. Daniel Mortlock and his colleagues has discovered this very first known quasar at redshift beyond 7 in 2011. Now you see the Lime alpha is in the Y band. And finally, these are the most distant quasars published so far at around redshift 7.5. These have been discovered by combining several latest instruments like dark energy camera on Blanco, VISTA, and WISE. So these are just how these most distant quasars published look like. What was most surprising is that they look quite similar to the spectra of local quasars, actually. The only difference is this sharp spectral break due to the IgM absorption, but the longer wavelength side, we basically see no difference. That means that the physical conditions around accretion disk and broadline region, at least these regions giving rise to rest UV, rest optical spectra didn't change much from redshift 7 to 0, including metallicity. Skip this. All right. And then we can also look at this figure on the vertical direction. This one, this very luminous one, was reported in 2015. What was surprising at the time was that actually this one was imaged by TUMAS, the old one. It was in the TUMAS images in TUMAS catalog for more than 10 years unnoticed since detected. And this year it was recognized to be a Heisey quasar. Now on the fainter side, these are the quasars we discovered from Subaru. Actually, I made this plot a few years ago, so the number of quasars is a bit larger now, but basically the same situation. So these are the quasars from Subaru observations, and in roughly half of the remaining time, I will be talking about this survey and the results from this survey. So at the time we started this survey more than 10 years ago, the known sample of Heisey quasars, you can see here, they're mostly limited to very luminous ones. So we wanted to go deep and find low luminosity quasars, which may be the main body of the whole quasar population, right? In the Losian Heisey universe, but we're interested in Heisey. So this survey has been enabled by this big camera called Hyper Suprime-Cam, HSC. And actually this guy, Satoshi Miyazaki, he's a PI of the camera. Actually, he was a builder of the preceding generation Suprime-Cam, which was still powerful. But after the success of that Suprime-Cam, he made a new one. This is Hyper Suprime-Cam. He's now a director of Subaru telescope. So we made this and put it as the focal, the prime focus of the telescope. And this is the biggest advantage of the HSC. It's wide field of view. So his a full moon. It's 30 square. 30 arc-minutes on the side. And for example, James Webb is powerful, but its field of view is not that small, but not that large. Actually, it's relatively small. It's kind of 10 scale arc-minutes like that. And wide field images on 8 to 10 meter class telescopes on the ground has typically up to a few tens of square arc-minutes or several tens of square arc-minutes. So it's like that. And compared to this, Hyper Suprime-Cam has a field of view of 1.8 square degrees, and it's like this. So you can imagine how it is powerful in surveying the sky, how fast its survey speed is on top of the sensitivity that is offered by the large telescope period of Subaru. It's 8.2 meters. So we use this camera to survey the sky. We started a program called Subaru Strategic Program, SSP. We were allowed to run one program when a new instrument is initiated. Actually, it is not guaranteed. We have to submit a proposal and must be accepted. So we studied this in a large collaboration in Japan, Taiwan, and Princeton. We used 339 for 7 years. It has been completed a few years ago. It has 3 layers wide. Our quasar survey is mostly based on light, and this went down to 26 mag over 1400 square degrees. This was a plan, and we actually achieved 1100. And deep, we went down to 27 over 27 square degrees, and ultra deep 28 over 3.5 square degrees. We use 5 filters in wide, G2 wide, and some narrowband filters in deep and ultra deep. And one of the unique features of this survey was its excellent image quality for ground-based observations. It's like 0.6 arcsec in I, 0.7 in Z, and 0.8 in Y band. So if you are familiar with ground-based optical observations, you would see how excellent it is for ground-based observations. And this is how we actually selected quasar candidates from the imaging data. So if you, for example, if you have a quasar at redshift 6, then its Lyme alpha is in the Z band. And in I band, we have a very deep IgM absorption, so it's very dark here. And we have quantity mixture here. So it is very red in I minus Z, and it's relatively blue in Z minus 1. So if you create a color diagram like this, then they come here, red I minus Z and blue Z minus 1. And at redshift 7, they come here. And stars are here. Here's the main sequence. These are brown dwarfs. So quasars are well separated from the stellar sequence. So you can, the simplest way would be to make a color cut like this, right? 6 and 7. But we adopted something one step advanced than that. We used a method called Bayesian probabilistic selection. So it's formulated like this. So we for every source, we calculate a probability that that source is a high-Z quasar. And that is PQ, which is a ratio between WQ and WQ plus WD. And here, W is kind of a weight that source belongs to, for example, this is a quasar high-Z quasar population, and this is brown dwarfs. When we are starting this, we assumed that all the contaminants are brown dwarfs, which turned out to be wrong, but this is how we calculate it. And now this, for example, the WQ or WD, this is a function of observed magnitudes, which is M, and also the fact that it is detected by the survey. And you can calculate this by integrating over these 3 functions over model magnitudes M and redshift or spectral type for brown dwarfs. And there are 3 functions here. This is the easiest. This is the detection probability for that model source, model mag, model Z, model spectral type. And the third one, this is basically this SED fitting. This is a probability that that model source would have the observed magnitudes. And finally, this one is a surface density. So this function accounts for the fact that if your source has colors similarly consistent with a high-Z quasar or with a brown dwarf, then you should think that it is a brown dwarf, because the surface density of brown dwarfs is much, much higher on the sky than high-Z quasars. Right, and this is the distribution of that PQ value for our candidates. We took spectra for all the candidates with PQ larger than 0.1, and for somehow we actually have spectra for these ones because these objects had in the past, they had a PQ larger than 0.1 with the older HEC data releases, older photometry. And it turned out that our selection is quite successful like this. This is again a bit old, but basically the same with the latest one. So as you can see, this peak at PQ of 1, it's dominated by high-Z quasars. So this is blue. And these are candidate narrow-line quasars. I will explain later. And these are this green. These are galaxies at ratio 6 to 7. So majority of the high PQ sources are actually at high-Z, and most of these are quasars. We have some contamination. These are also emitters at ratio around 0.8 to 1. And this red, these are brown dwarfs. And if you look at this peak, this is actually dominated with brown dwarfs, which is exactly what you would expect. Okay, and this is just an atlas of what we have discovered so far. Actually, we have some more in the latest discovery paper, but in total, we discovered something like 200 quasars at ratio 6 to 7. And from this sample, we did several things. One is, of course, establishing the quasar luminosity function. So we published our quasar luminosity function at ratio 6 in 2018, and then at ratio 7 in 2023. So we found that, for example, the overall shape of the quasar luminosity function doesn't change much from ratio 4 to 7. These are kind of self-similar to each other, but the overall amplitude decreases significantly. From 4 to 7, it's like a drop in amplitude by more than 100. We knew that the number density is decreasing to a higher redshift, and we knew that the rate of that decline is actually maybe becoming high. It may be accelerating at redshift beyond 5 for the most luminous quasars. But now with this luminosity function, we have confirmed that that kind of accelerating decline of the number density is also happening in the moderate luminous and also low luminosity quasars. So it's a kind of general trend. And also from the large number of objects we discovered roughly 200, we spotted some rare cases. For example, this is a pair of objects at ratio 6.05. We found 2 of these very red sources. Actually, this is the discovery was actually serendipitous. We found this one, this C1, in a normal routine. But when I was making a presentation material and when I was cut an image of 100 quasars known at that time, I just noticed that there's something here, similarly red. So we put long slit like this over the 2 sources, and then we got something like this. So clearly, these are at the same redshift. These are Lyme alpha at around 8500 angstroms, and this Lyme alpha not that very broad, but not that very narrow. And these are the 1D spectra of the 2 sources. The Lyme alpha has a broad wing of 1500 kilometers per second. And we concluded that it's most likely that the both galaxies host quasars. And what is more interesting is that we took ALMA data for this system. This is ALMA image. So in color background, this is C2 line emission. In contour, this is far infrared. So this right one, this C1 is here. So it's bright. And this C2, this is similarly bright in optical. Actually, it's 1 mag fainter, but more or less it's comparable. And this one is here. So actually, this one is very faint. It's even fainter than this gas structure bridging these 2 sources. And we have also found some structure that we call tail. So our conclusion is that these two galaxies are merging with each other, and somehow this region, the star formation rate is very high, but this region, the star formation rate is very, star formation is not that active. And for the sample, we are also trying to collect a black hole mass and also host galaxy properties originally from the ground. So we used Subaru, Gemini, and VOT and others to collect near-infrared spectra like this and measure black hole masses. And on the other hand, we used ALMA over multiple cycles to measure dynamical mass, gas and dust mass, star formation rates, outflows, and so on. And actually, the detection rate with ALMA is quite high, even for our low luminosity quasar sample. And we got something like this. So this is a dynamical mass from ALMA, which we think is a surrogate for the host stellar mass. And this is black hole mass. And this dashed line is a local Comedian correlation. And these red circles, these are low luminosity quasars from our survey. The color represent rest UV luminosity. So we think that we know that the scatter is large and there are some lower limits, but we think that the low luminosity quasars are not inconsistent with local relation. But we know that luminous quasars are here above the local relation, which may indicate the fastest growth of supermassive black holes compared to the host galaxies. But one of our colleagues has demonstrated that actually one can reproduce this distribution by combining this local relation and also intrinsic scatter of this relation, and also scatters coming from observation errors, uncertainties, and also selection bias, because these are very luminous quasars, selected by shallower surveys than ours. So it is subject to strong selection bias, and she concluded that by combining these various effects, actually you can reproduce this distribution from this relation. Okay, and now we have James Webb. So we are trying to collect information from James Webb, and this is a work led by our colleagues Shuen Ding, Masafusa Onoue, and others. So here we have observed 12 of our objects. These are the observed data of the quasars, and these are the data minus point source model. So you clearly see the residual extended emission, which comes from stars. And the bottom, I think this is the easiest to see. This signal to noise map of the extended. So we have detected host stellar emission from a significant fraction of these objects. And we found that actually our low luminosity quasars are very good laboratory to study the host galaxies, because the quasar to host radiation flux contrast is not that extreme as in classical luminous quasars. And also, we took NewCam spectra, and in these two cases, so our original purpose was to measure black hole mass from Balmer lines like H alpha, H beta, but actually we found that we see some stellar absorption lines like this on top of kind of usual quasar spectra. And from this absorption spectra, we can estimate the star formation history along with this information from the imaging dataset. And what we have concluded is that in these two quasar host galaxies, the major star formation episode has been finished, and these are kind of towards, I think we said that they are quenched already, or quiescent. Okay, so that's about unobscured quasars from our survey. So we can review various surveys again on this plot. So this is a quasar luminosity function at ratio 6. So these dots are quasars, and these open symbols, these are galaxy luminosity functions. And on the vertical axis, this is a number density, but you can convert this to the area that contains one quasar. Okay, so if the surface density, number density is here, then you would need 1 scale degrees to find a single quasar. If the surface density is number density is here, then you would need 10 scale degrees to find a single quasar. So as I mentioned, Sloan Digital Sky Survey has covered the luminous end. It went very, very wide to cover this end. And more recently, Quasars covered this range, basically the luminous end. And several years later, the CFHT survey has covered this space. They went deep, but over a much smaller area. But it was okay because the number density is much higher here. The luminosity function known at the time is like that. So we knew the luminous end fairly well, but we didn't know whether it goes up like this or it flattens like this. And our HGC survey has covered down to -22 or -21 and measure this luminosity function as wanted. But recently, most recently, we learned that actually this was not the end of the story at all. Now we have James Webb, and the original expectation was that James Webb was not that powerful in this field because it can go very deep, -18, -17, but the area field of view is not that very large, right? So any reasonable survey with James Webb can cover an area like less than 0.1 scale degrees. But if you look at this luminosity function, extrapolate it this way, then this tells us that even at the depth of James Webb, we would need at least 1 scale degrees or a few scale degrees to find even single quasar. So we expected that James Webb was not able to find even single quasar, single AGN from a blank field, randomly chosen field observations. But of course, as many of you know, that was wrong. It discovered many faint AGNs, or some people would say it's a candidate AGNs. But basically, they are faint galaxies in the high Z universe, and in the rest optical spectra, they have broad component in Balmer lines. And since it is difficult to make this broad component exceeding 1,000 or 2,000 kilometers per second with normal star-forming activity, the common interpretation is that they are coming from broader region of AGNs. So we learned it's actually like this. So these are, again, faint James Webb AGNs, number densities, and we still don't understand what is happening here. Why we have such a large gap here, and whether these are really the, basically belong to the same population with this one. We still don't understand. And we think one of the keys would be in this intermediate luminosity range, right? This may hold a key to find some link between the two. And of course, we have many objects coming from HSC in this intermediate luminosity range, and we are trying to investigate these objects more here. And we are trying to persuade people that we need more telescope time with James Webb and others. And I will, in most of the remaining time, I will talk about one of such projects in this intermediate luminosity range. So again, it's redshift versus rest UV mag, and these are luminous quasars, and these are quasars we discovered. But when we were looking for these quasars, we also discovered galaxies, luminous galaxies, which are basically contaminant to our survey. But we found that a significant fraction of these galaxies have very luminous line malformation, about 10 to the 43 ELX per second. The spectra look like this. So they have very strong but narrow line alpha. So we cannot say that they are quasars because the line alpha width is too narrow. But we suspected that maybe some of these may host, AGNs that are not visible in the rest UV, so obscured AGNs. Because at such high line alpha luminosity, at the lower Z universe, we know that a significant fraction of these galaxies have AGN inside. For example, this is at redshift 2, and this is line alpha luminosity. And if the line alpha luminosity of a galaxy is above 10 to the 43, then if you look at this right panel, the AGN fraction is above 50%. And we don't know whether this is also true at redshift 6 to 7, but this is kind of encouraging. So we further pursued whether they are really AGNs or not. And we, for example, took Keck Mossfire spectrum on one of these objects. This is led by myself from Norway. We spent a fairly good amount of time, 2 hours in Y and 4 hours in J. And we detected here the doublet C4 lines. We are pretty sure that these are real. And if you make a plot like this, this is C4 equivalent width and C4 over line alpha. These are all basically AGNs, and this is our object now here. And this line is a threshold between AGN and star-forming galaxies. You can basically, from photoionization models, you cannot produce such high equivalent widths of C4 without AGN. So it is one of the evidence that we think that there might be AGN inside. But there's also counter evidence. We observed these 4 of these objects with Chandra with a 60 kilosecond per target, hoping that if these are really obscured AGNs, we will find some signal. But as you can see, there's a really no detection. We have marginal detection here, but basically it's no detection. So then this may be telling us that actually they are not AGN, right? If they are AGNs, our expectation that we would find signal, statistically significant signal. And actually, these results have been already posted on arXiv. Kazushi Iwasawa-san wrote this paper and possible interpretation of that. And we also observed these objects with James Webb. We use NeoSpec. In cycle 2, we observed 10 of these with the highest line alpha luminosity, about 10 to the 43.5. And also in cycle 1, we had similar objects in our sample. 3 of these objects are similar properties in line alpha. So in total, we have 13 objects with NeoSpec spectra over 2.9 to 5.1 micron. And these are the spectra we got. So from 2.9 micron to 5.1 micron, it's a bit hard to see, but here's the H alpha, and you see that at the base of H alpha, we clearly detected broad component, as in other faint James Webb AGNs. And the fraction of this broad line is actually quite high, as you can see. And we also detected this broad component in H beta, H gamma, and other Balmer lines, as well as helium, as you can see here. But never in forbidden lines, never in O3 and other forbidden lines. So again, as in other James Webb objects, we concluded that this is coming from broad region of AGNs. But again, what is surprising is that the detection rate is quite high. It's 9 up to 13, so the AGN fraction is 70%. And we have also estimated the black hole properties, and black hole mass is like, so from broad components, the black hole mass is something like 10 to the 8 to 9. This is the Eddington limit. So they are shining at well, close to the Eddington limit, or slightly sub Eddington. From Balmer decrement, we estimated the dust extinction, which is 1 to 2 mag, which is moderately obscured quasars, right? But if you convert this to extinction at the line alpha wavelength, then it's at least 6 and up to 13 mag, which is a lot. And this is a reason why we didn't see quasar signatures when we took rest UV spectra from the ground. That's why we classified these objects into galaxies when we discovered them. But by looking at the rest optical, where the dust extinction is less significant, we found that they're actually AGNs inside. Okay, we have also looked at their morphology, and basically, okay, so on the bottom panel, so these are 3 objects we have NewCam data, and these are the point source subtracted, so basically extended emission of these 3. So you see extended emission in this one, but these 2 sources are dominated by point sources. And for the remaining 10, we have NeoSpec target acquisition images. And if you look at this, the 7, G01 to G07, these are basically compact. This is a PSS model. But the remaining 3, these are extended. And if you compare this with the spectra, with the detection of broad lines, then we find that actually all the compact sources have broad lines. Okay, 1, 2, 3, 4, 7 plus these 2. All the compact sources have broad lines, and all the extended sources do not have broad lines. So this is not a coincidence. It's surely driven by physics, and our interpretation is that these objects with broad lines, the broadband flux is also dominated by AGNs, whose radiation comes from unresolved nuclei. So it's another evidence that they are AGNs inside. you skip this, we have found that some of these objects have colors consistent with red dots. They have fairly red or rest optical colors. And this one is a number density. We have estimated the number density of AGNs from our sample, which comes here. So this is lower limit because we observed only the brightest line alpha emitters, and our original SHELLQ selection was not optimized for this kind of obscured quasars. But still, this is comparable to number density of unobscured quasars we were originally looking for. That means naively that the obscured fraction must be 50% and maybe much higher than 50%. Okay, this is giving you what's that? Yeah, so these are luminous quasars and these are faint James Webb AGNs. And again, our objects are here, and the targets of these James Webb observations are marked by larger circles. Those with double circles are broadline detected sources. This is just showing that again, our SHELLQ sample as a whole is in a very unique and interesting luminosity range between classical luminous quasars and these faint James Webb AGNs. And indeed, these objects I just presented have rest UV properties that are like lower luminosity quasars, right? They are discovered. No, I'm saying wrong. I'm sorry. They are galaxies, the rest UV, but the rest optical, they are more like James Webb AGNs. All right. In the remaining 10 minutes or so, I think I will touch on some future prospects, mostly at Subaru. So at Subaru, a new instrument next to HSC is coming online. Actually, it has already started operation, which is Prime Focus Spectrograph. It's a large instrument. It's a multi-object spectrograph composed of several pieces. So this is one of the most important one. It is Prime Focus instrument, which houses fiber positioners. We have 2,400 fibers with this instrument, and it is combined with the wide field corrector. This one is actually shared with Hyper Suprime-Cam. We use this for Hyper Suprime-Cam as well, and these are combined like that and put. It is kind of placed in the air, but supported by the structure. But it is here at the focal, at the prime focus. And actually, this is the reason why we cannot use HSC and PFS together, because HSC also needs this one, but of course, this one can be used only for PFS or HSC. And of course, another reason is that they're too heavy, right? We cannot place both of these such heavy elements here. Even putting single PFS or HSC here is actually a very tough work. And observatory, you're always, complaining about how hard it is. But so we have this one, and starlight or galaxy light comes in. Here's a primary mirror and comes in this way, and light is sent by fibers here to the Nasmith focal plane here. So we have, this is a kind of a big room, and this room we have this 4 spectrograph module, and each of these 4 spectral modules have 3 arms: blue, red, and infrared, and take spectra. So this is how the actual that Nasmith room look like. So we have 4 spectral modules, and each of these have 3 arms. I don't know which of which is, but blue, red, infrared, blue, red, infrared. So we have 4. And we saw this slide before, but this is about the field of view. PFS has this size field of view. So it's smaller than HSC, but it's more or less comparable. So it's 1.3 square degrees, and it's 2,400 fibers. And this is how a single PFS data frame would look like. This is from commissioning run. So here on the vertical axis, the fiber index run from 0 to 2,400. So each row is 1 spectrum. Okay, so we have 24 spectrum like that. From 0.4 micron to 1.26 micron. So you can imagine that how powerful it is. We can take your favorite 204 objects in scattered over a 1.3 square degree field of view with a sensitivity of 8 meter class, 8.2 meter mirror. And of course, in the European community, you have moons and VOD. It's a rival of PFS. They are competitive, but also complementary moons extend to 1.8 micron, 1.8, 1.9 micron. So it's wider in the wavelength coverage, but the field of view of PFS is much larger. It's 1.3 square degree. And also the fiber density is higher in PFS. So again, it's complementary and also competitive. And actually, when we are building this PFS, there was a suggestion to change the name because PFS is complicated, confusing. People always make mistake calling them PSF, right? We have to make competition like, okay, PSF or PFS is improving, something like that. So we have discussed about that, and there was a suggestion. Actually, I think that was suggested by Robert Lafton of Princeton, if you know him. He suggested that we should name it SUNS, S-U-N-S, Subaru Nighttime Spectrograph. Apparently, it is to beat moons, at least in day, and we didn't take it. It is still PFS, and I think that's a format now. Okay, so with this PFS, we are now starting a new SSP survey. As I told you, once we have a new instrument, we are allowed to propose one SSP. Well, we are allowed to propose many SSP programs, but the observatory will approve only 1 or 0 program. And this one is approved. So this one is, again, a very large program. We will use 360 nights over 5 to 6 years. It has started this spring. It has 3 pillars. In cosmology pillar, we have 4 million auto emission line galaxies that ratio from 0.6 to 2.4 to explore the dark sector of the universe, dark matter, dark energy. And we have galaxy evolution pillar, which include AGNs. We aim to observe 0.5 million continuum or emission line galaxies, that's ratio 0 to 7. And finally, galactic archaeology. Milky Way, its outer disk, halo, its dwarf galaxies, and M31, M33. And of course, we have some AGN component, of course, selection optimized for AGN. But even without that, you would imagine that we have this many galaxies, and certain fraction of these galaxies must contain AGNs, right? If it is 10%, we still have many. And I would expect that because these are emission line galaxies, so the AGN fraction would be higher than 10%. So I think we will have a lot to do with this data for AGN science personally, but for many purposes. Okay, this is how the galaxy evolution field of the SSP survey looks like. So we will observe Cosmos, XMM, LSS, Deep 2-3, EDSS, and N1. I think in total 15 square degrees. And this is showing that 15 square degrees can be covered by only 11 PSF. Now, I won't explain this in too much detail. This is galaxy evolution survey targets. We have a few classes of targets, continuum selected galaxies, bright quasars and background galaxies for IGEM tomography, and also Lyman factors. Okay, and I think this is my last slide. This is more general future prospects from a high quasar view. So our focus is now clearly on the redshift beyond 7 or 7.5, right? We know that at the fainter side, the James Webb is so powerful that it's probing many low luminosity agents. But bright quasars, they're somewhat different from, for example, from the science perspective. If we are interested in the most massive galaxy, most massive black holes in the universe at that redshift. And of course, you're much familiar with than I am, but now Euclid is operating and it's surveying the sky. I am a part of the Euclid. Its policy doesn't allow me to say anything, but I think many of you know the rumor that and we will see very soon, the new redshift record. And Roman Space Telescope is also coming online. It will be launched next year or a few months later, and we'll explore basically the deeper universe, but over a smaller area. And we find many quasars again, up to redshift 9 to 10. So I think the future in this field is bright, maybe too much exhaustive, but of course, for example, there are obscure populations that cannot be truly probed by this mission. and I think there are many from we can learn from X-ray and other multi-wave length observations. So I think I will stop here. Thank you very much.
Thank you very much, Yoshiki. So there's many questions, but we can discuss later. So I leave